Hey there, deep divers. Ready to jump into some AI? We're going deep on abstract reasoning today. The kind of puzzles that humans can usually solve without breaking a sweat.
Hmm.
But computers, well, they haven't had it so easy.
Yeah, abstract reasoning has always been a tough nut to crack for AI.
Exactly. But that might be changing thanks to something called test time training, or TTT for short.
TTT.
Yeah, it's kind of like a student learning during the test itself to ace it. Sounds crazy, right?
It is a pretty wild concept when you think about it. I mean, we're talking about models that adapt and learn in real time, not your typical machine learning scenario.
Definitely not. And for this deep dive, we've got a whole stack of research papers from MIT. They've been doing some really fascinating work with TTT.
Oh, yeah, I've been following that research too. Some pretty exciting stuff.
For sure, neural networks matching human performance on visual reasoning puzzles. TTT boosting accuracy by like 6 times. We'll unpack all that and more, but first, I think we need to set the stage a bit.
Absolutely. We need to talk about the Abstraction and Reasoning Corpus. ARC for short. It's like the ultimate proving ground for testing AI's reasoning abilities.
Okay, so ARC, visual puzzles, I took a peek at some of them, and let me tell you, they're pretty brain-bending. What do they actually look like? And what makes them so tough for AI?
So imagine a grid, kind of like a simple pixel art image, but with colored shapes. You get an input grid and an output grid, and the goal is to figure out the rule that transforms the input into the output.
Got it. So it's like, here's the before, here's the after, now what's the magic trick?
Exactly. And the trick can involve all sorts of things, counting shapes, reflecting them, even simulating something like gravity. But the real kicker is that these puzzles are designed to test how well a model can handle brand new problems, not just ones it's seen before.
So it's not just about memorization, it's about understanding the underlying logic and applying it to new situations.
Mhm.
That sounds a lot like how humans reason.
You got it. And traditionally, there have been two main ways AI researchers have tried to crack this kind of reasoning. One is program synthesis. It's basically about building a set of instructions, kind of like a computer program, that explicitly defines the transformation rule.
So giving the AI a step-by-step recipe to follow.
Right. The other approach is what we call purely neural. It's all about training a neural network with mountains of data and hoping it implicitly learns the reasoning patterns.
So two very different philosophies, but you're saying both have limitations.
Yeah, they both have their strengths and weaknesses.
Hmm.
Program synthesis can struggle with ambiguity and unexpected variations. And purely neural approaches can be black boxes. It's hard to know why they make the decisions they do.
And that's where test time training comes in.
Right. Instead of relying on a fixed set of rules or just crossing your fingers that the AI figures it out, TTT lets the model actually learn and adjust during the test itself.
Okay, I'm definitely hooked. Let's get into how this TTT magic actually works. What are the secret ingredients?
Well, there are a few key ingredients that make TTT so effective. And the first one is initial fine-tuning.
Fine-tuning. You mean like giving the AI some practice before the big game?
Exactly. Before being thrown into the ARC puzzles, the researchers gave their models a warm-up with some synthetic data. This data involves similar reasoning tasks, but was specifically designed for training.
So it's like training for a marathon. You wouldn't just show up on race day without any prep.
Right. That's a great analogy. But there's a really interesting twist here. They found that using data generated by another language model actually hurt performance.
Why would that be? If a language model is creating the data, shouldn't it be even more helpful for training?
You'd think so, right? But it highlights the importance of data quality. Just because a language model can generate data doesn't mean it's good data for training. In this case, the data from the other model seems to have introduced some kind of bias or noise that actually messed things up.
So garbage in, garbage out, even in the AI world. Got it. What's the next ingredient?
So the next one is what they call an augmented TTT dataset. It's a clever way to give the model multiple perspectives on the same problem. Imagine trying to understand a 3D object. You wouldn't just look at it from one angle, right? You'd walk around it, turn it over in your hands, get a feel for its shape from every direction.
I'm starting to see where you're going with this. You're saying they're showing the AI different variations of the same puzzle, like rotations, flips, maybe even changing the colors around.
You nailed it. They use these transformations to create a whole bunch of variations for each puzzle, and it worked wonders. This trick alone boosted accuracy by a whopping 55%.
55%. Whoa, that's a huge jump. Just by showing the AI the problem from different angles, they managed to significantly increase its reasoning ability. Okay, color me impressed. 2 secret ingredients down. What's the final piece of this puzzle?
The final ingredient is all about personalization. Instead of having the model learn one general adapter, think of it like a universal toolkit, they found that having it learn a specific adapter for each task significantly improved performance.
So it's like having a custom-made tool for each puzzle, rather than trying to use a one-size-fits-all approach.
Exactly. It's as if the model gets a personalized tutor for each challenge. This allows it to fine-tune its approach and master the task at hand.
I'm loving this TTT stuff more and more. But, okay, how did it actually perform on this ARC challenge? Did it live up to the hype?
Oh, it did. In some pretty spectacular ways. But I think we should save that story for after a quick break.
Welcome back, Deep Divers. Before the break, we were talking about the 3 key ingredients that make test time training so effective. So now let's see how this all plays out in practice.
Yeah, you mentioned earlier that TTT actually closed the performance gap between smaller and larger AI models. That sounds pretty groundbreaking. What's going on there?
So the researchers put TTT to the test using different sizes of the Llama language model. They tried it out with models that had 1 billion, 3 billion, and 8 billion parameters.
Parameters, those are like the connections in an AI's neural network, right?
Yep.
More parameters, more brain power. You got it. More parameters usually means the model has a greater capacity to learn and process information.
So a model with 8 billion parameters, that's like the heavyweight champion of AI.
You could say that. But here's what's really cool. TTT helped the smaller models, those with just 1 or 3 billion parameters, punch way above their weight. They started achieving performance levels much closer to the 8 billion parameter giant.
Hold on, so even a relatively lightweight AI can compete with the big dogs thanks to TTT.
Exactly. It's a bit of a David and Goliath story in the world of AI. TTT helps level the playing field, allowing smaller models to hold their own against the heavy hitters. And this is great news because it means we might not always need those massive, energy-hungry AI models to get impressive results. Smaller, more efficient models could be just as capable with the help of TTT.
Okay, I'm seeing the appeal here. Efficiency and performance, that's a winning combination. But how did TTT actually stack up against the best of the best? You know, the existing state-of-the-art methods for solving those ARC puzzles. Was it able to hold its own?
This is where things get really interesting. The researchers compared their TTT approach to other top contenders on the full ARC dataset. Remember, we're talking hundreds of these brain-bending visual puzzles specifically designed to test AI reasoning.
All right, don't keep me hanging. How did it do?
Well, on its own, TTT achieved a remarkable 47% accuracy.
47%. Not bad at all, considering how tough these puzzles are.
Right. But then they took it a step further. They combined TTT with a top-performing program synthesis system called BARC.
Wait, so they blended the neural network approach of TTT with a more traditional rule-based approach.
Yep. It's like combining the intuition of a seasoned detective with the precise logic of a computer program.
I like that analogy. So what happened when these two approaches teamed up?
The results were phenomenal. Together, TTT and BRR achieved a groundbreaking 61.875% accuracy on the full ARE dataset.
Hang on, that number sounds familiar.
It should. That's average human performance on ARC.
Whoa, so they actually managed to create an AI system that can reason at a level comparable to us humans.
That's right. It's a huge milestone, and it suggests that the future of AI reasoning might lie in these hybrid approaches. Combining the flexibility of neural networks with the explainability and structure of symbolic systems could unlock some truly next-level AI.
I'm mind blown. But before we get too ahead of ourselves, I think it's time to pop open the hood and look at the technical nuts and bolts of TTT. We've been throwing around terms like adapters and augmented data sets. Let's break those down a bit further.
Sounds good. Understanding the mechanics will definitely help us appreciate the true power of TTT. So let's start with those augmented datasets. Remember how we talked about them being like showing the AI a puzzle from different angles?
Yeah, I remember the 3D object analogy. But can you give me a more concrete example of how this works in practice?
Sure. Let's imagine a super simple puzzle where you have a blue square that moves one position to the right in the output grid. Now, picture rotating this entire puzzle by 90 degrees. The relationship between the input and output is still the same. The square moves one position to the right, but visually it looks completely different.
Ah, got it. So even though the image looks different, the core logic stays the same.
Yeah.
Essentially, they're teaching the AI to see past those superficial differences and focus on the underlying pattern no matter how it's presented.
Exactly. And they use all sorts of transformations, not just rotations, flips, color swaps, you name it. They create this rich and diverse training set for TTT so the model learns to home in on those abstract relationships, not get distracted by surface level stuff.
Really clever. But, okay, what about those task-specific adapters? You said they're like personalized tools for each puzzle. How do they actually work?
Think of a large language model like a massive network of interconnected neurons. These neurons are responsible for processing information and making decisions. An adapter is like a small, specialized module that you can plug into this network.
Ah, so it's not about overhauling the entire network. It's about making small tweaks to optimize for a specific problem.
Precisely. And the cool thing is that the model can learn a different adapter for each new problem it comes across. It's like having a Swiss Army knife of reasoning skills, with each adapter being a specialized tool for a specific job.
Okay, that makes sense. But learning a new adapter for each task, wouldn't that take forever? How do they make it work so efficiently?
That's where a technique called low-rank adaptation, or LoRa, comes into play. Instead of updating all the parameters in that massive language model, LoRa lets you fine-tune things very efficiently by focusing on just a small subset of parameters. It's like a surgeon making a precise incision, targeting only the area that needs adjusting.
Effective and efficient, that's a powerful combination. But one thing that keeps popping into my head is, you mentioned that TTT allows the model to adapt during the test itself. How does that actually happen? Imagine the AI is staring down a brand new ARC puzzle it's never seen before. What happens next?
That's where the real magic of test time training comes in. It's all about thinking on its feet, adapting in real time.
Welcome back, deep divers. Before the break, we were getting into some of the really fascinating stuff about how test time training works, especially those task-specific adapters. But I really want to understand how TTT tackles a brand new puzzle that it's never seen before. It's like the AI is going in blind, so how does it figure things out?
It's a great question, and this is where TTT's adaptability really comes into play. Remember all those transformations we talked about? The rotations, the flips, the color changes? Those are crucial for how TTT handles these new puzzles during the test.
Okay, yeah, I remember. But I thought those were mainly for training the model.
They are used during training, but they're also cleverly incorporated into what the researchers call an augmented inference pipeline. So here's the thing. Let's say our AI is facing a brand new ARC puzzle. The first step is to generate multiple versions of that puzzle using those same transformations. So they might rotate it, flip it horizontally, maybe even swap some colors around, all while keeping the underlying logic of the puzzle intact.
So it's kind of like the AI is examining the puzzle from all these different angles, trying to get a more complete understanding.
Exactly. It's like getting a second, third, fourth opinion all at once. Now, the model makes a prediction for each of these transformed puzzles. And because all those transformations are reversible, they can then undo the transformations on the predictions to get a set of predictions for the original untransformed puzzle.
Got it. So now they have a whole bunch of different predictions for the same puzzle. What do they do with all of them?
Here's where it gets even cooler. They use a voting strategy to combine all those different predictions. It's called self-consistency. Basically, the AI is checking its work by looking at the problem from a bunch of different perspectives and seeing which answer comes up most often.
So the AI isn't just randomly picking an answer. It's actually considering all these different perspectives and going with the solution that makes the most sense across the board.
You got it. And this self-consistency thing, it's incredibly effective. It turns out that some transformations actually make certain parts of the puzzle easier for the model to figure out. So by combining all these different perspectives, they can achieve a much higher level of accuracy.
I am so impressed with this whole approach. But let's step back for a second. We've been talking about all these technical details and the crazy good performance on the ARC data set. But what does it all really mean? What are the big takeaways here for our listeners?
I think one of the biggest takeaways is that test time training really is a paradigm shift in how we think about AI. Traditionally, we train models on these massive data sets and then deploy them with a fixed set abilities. But TTT turns that on its head. It's like asking, what if AI could keep learning and adapting even after its initial training? What if it could actually get smarter over time?
Like it's got this built-in growth mindset, always learning, always evolving. That's a pretty powerful concept.
It is. And think about the potential applications. AI that can solve complex scientific puzzles, personalize education to each individual student, even assist doctors with diagnoses by adapting to each patient's unique circumstances.
Wow, those are some game-changing possibilities.
Hmm.
It really feels like TTT could be the key to unlocking a future where AI isn't just intelligent, it's adaptable and
Mm.
truly helpful to humans.
Absolutely. And I think it also highlights just how much we still don't know about intelligence, both in humans and in machines. Even with all the incredible progress we've made in AI, we're still just scratching the
Hmm.
surface.
It's a good reminder that understanding intelligence is a journey, not a destination. TTT is an amazing step forward, but it's just one step on this crazy, exciting path of discovery.
Couldn't have said it better myself.
Yeah.
So on that note, we'll leave our listeners with a final thought-provoking question. If AI can already match average human performance on a benchmark like ARC, what other human-level cognitive abilities might be within reach? What breakthroughs are just around the corner?
That's a question that'll keep me thinking, for sure. Thanks for joining us for this deep dive into the fascinating world of test time training. And until next time, keep exploring, keep questioning, keep diving deep.